derivative of ln is 1 over the thing inside. Chain rule says the thing inside gets a turn too. So I already did ln's derivative. That's what ln's derivative is. What's the derivative of this? Beautiful. And we just told ourselves. And what's really nice about that? These go away. And what's the limit now? Let me stop there. Did you guys see that? It's almost too good to believe. But this guy is the same as what's inside there, so it shouldn't be surprising that the chain rule piece will cancel with that after the derivatives. They agree with each other. So the derivative of the top is there. Derivative of the bottom is there. This is the one time you're allowed to take the derivative of each separately because it's a process. I'm not doing the derivative of this. I'm applying L'Hopital's rule. And then when I let x go to infinity, what happens to 1 over x?
0.
Good. And so I get the limit is 1. And that's the limit of ln of y. So ln of y goes to 1. So y goes to e. And this is actually a definition of e. This is the preferred definition of e for most textbooks. To me, it's going to be weird for me to say, but it's kind of dry.
So at the beginning, when you change the 1 plus 1 over x, when you change it from a 1 minus 1 over x, that changed it from...
That changed it. Let me see if can you guys pick up on what that changed?
Yes,
Remember what we say? If it was 1 to a power, it's always 1. But why is it not that? Because it's always a little more than 1.
Yeah.
So if I had 1 minus that, it'd always be a little less than 1. You guys kind of with me? So then it would still... Well, I wanted to also do the e. I wanted to do the definition of e.
Okay.
So it's still a question about... and this is kind of important. Why is 0 to infinity not indeterminate?
It's equal to 0 is 0.
In fact, anything less than 1 to the infinity is not indeterminate.
0.
Because it's always going to be 0. It just is. What do you get when you do 0.9? Try this in your calculator. Who's got the calculator out? Do 0.999 to the millionth power. See if your calculator freaks out. Let me try it.
My calculator is broken.
Well, as you're getting it out, that I have nothing to do with me. Just my calculator felt what was going to happen.
It's punched 3.70152079 e to the negative 44.
Cool. You guys get that?
Yeah.
I like it. Cool. And e negative 44 means it's basically 0 for any human. Right? So if you did it to the 10 millionth power, so I mean, anytime you multiply a number less than 1 by itself, you're going to get a smaller number. Of course you are.
It's just another 0. Yeah, I think.
Yeah, you add another 0, it's going to be 0.
Wow, trippy. Like what?
Do 10 million instead of, because the calculator gives up.
Yeah.
It gets so small, even the calculator's like, that's 0, man. So it's not really 0. It's not really 0. It's just outside the bounds of its abilities to differentiate. Anyway, okay, that was a little bit.
So if it was 1
Left to
minus
right.
1 over x, we just immediately say 0.
No. Okay. So, what would happen if I made it minus? Where would it change? Minus, it would change the signs here, right? There, but then this would still be that,
Negative.
right?
Negative 1.
So it gets interesting. It won't be negative 1, I don't think, because this would have still would have been negative at the end. I think, if I'm thinking about it right, it's still going to come out to be 1, but it's still a question. It's because what we don't know is if the inside, if in this case it's not getting to 1 fast enough, then this is going to happen. And it's going to go to 0, or some number less than 1, right? But this went to 1 fast enough, faster than this went to infinity, so it came out to 1. It would.
Okay.
Maybe. And if you don't trust me, you can just do it. The same way we just did this. All right, so long story short, sure, I can give you one of those. That was the question. Sure, I can give you one of those. You just have to know you got to apply a natural log so you can pull that ugliness down. I can't handle freaking x power. Screw that shit. If you look back at your earlier test, I gave you one that was like x to the x, something like that. X to the cosine x, maybe even, some of you guys. Okay. Oh, did I gave you guys the answer key right?
Yeah.
Or part 1. So part 2 will be coming tomorrow with your grade sheets. You guys know there's a workshop tomorrow. What time is it, Danny? 11 to 1, I think. So if you want to go to that, this is not a bad idea. Corey's a really good teacher. If you know Corey Manchester, he's the one that's running it. Yes, he teaches at State also. So if you want to do that, it's great. It's no problem. You can come to the class late, or you can just leave there early and come over. It's up to you guys. I don't care where you get it to make sense. I just care that you get it to make sense. So if a book or something else, or some review book that you get from Barnes & Noble or something makes more sense than I do, kick ass. Something's got to make more sense than I do.
Where's the workshop at?
Do you know? Do you remember?
That's on the phone. I can look it up.
Okay.
On the door outside.
Oh, it's okay. Yeah, they have the whole final exam workshop schedule out there.
It's only 36 months, room 30 seats.
Yeah.
All right.
Doing 36.
Will we do something with endpoints?
36 is the one.
On the other side of the science building.
Yeah, the one just like this over there.
Okay.
Yeah. All right. So we have anything else for today?
Anything with endpoints? Will we do something with endpoints? Middle?
How do you mean endpoint? Oh, you mean like Riemann sum kind of stuff?
Are we going to do like
Probably not, to be honest.
Okay.
Don't. Well, let's see.
Would we have to do the long way, or can we just let the integration question?
So the only reason I could ask you a problem like number 1A is so you don't forget where derivatives came from, or like we had the epiphany earlier. When you're doing specific little detailed problems, you sometimes forget the idea behind it. You have to constantly remind yourself what things mean, and that's why I've been kind of big about this whole. What does this mean? Tell me what this means. What the hell? You're like, it's just a number. Leave me alone. Shit, is it right? But you got to remember why things work the way they do, where they came from. So why are derivatives slope? Because that's how we built it. We built it off of slope. So of course it's slope. That's all it is. Yeah.
How many questions so far?
I don't know.
One really.
So it can't be like a lot longer, but we are going to have another half hour than normal, right? We're going to have 2 hours for this. So I'm just going to go crazy and just no. Normally my finals are, well, I don't know for calc. It's like I think a normal test is like a total of 18, 20 questions roughly for us. So this one could be somewhere like 25. Counting A through whatever, right? I hate when linear approximations. Could be. Okay.
What about calculus on the front?
Oh wait, you asked a question, right, John? About endpoints?
The 23 endpoints?
Oh yeah, not really. Don't worry about that.
What about Newton's method?
Second.
Newton's method.
Oh, Newton's method, maybe. But remember, what did I do for you on the test?
He gave us.
I gave you the thing, man.
Oh, that thing.
So then you just got to plug and chug.
Plug and shut.
You just got to make sure you're plugging in the right stuff. Find a linear approximation for what function you want to look at.
One that you
That could be anything.
hard.
We've done the square root, right? What about ln?
Ooh.
So another way to interpret this question is the exact same question. Find the tangent line for this function at x equals 0. Because the tangent line is the linear approximation. So that whole section could have been worded differently. But they want to show you how you can look at something different, how you can use what you've done before for different reasons. So we are constructing a function that represents this function when it's close to 0. A much better function. A linear function. And one thing you learn in 280 is how you make polynomials that fit it even better. for longer. So if you don't stop at linear approximation, you make a quadratic approximation, and then it's able to curve and fit this better for a longer range of values. Does that make sense what I'm saying? So remember there's that one part, I'm not going to probably put on the test, but we had to figure out how long the approximation was good to within 0.01 or whatever. You guys remember doing that? We had to do the sandwich and look to see when it hit the ceiling or the floor and see how long was it good. Sort. But if you go to higher powers, if you do quadratic fits, if you do cubic fits, whatever, then they're able to fit better for longer. So in 280, you actually do an infinite polynomial. Ooh, yeah. So, all right, something to look forward to. If you don't, it's too bad. You'll never know what I'm talking about. So, if you realize all I'm asking you to do is find the tangent line, that is something you got to be able to do. Can you find the tangent line? Look at it like that. If I say this, say, okay, I'm going to find the tangent line, because that's what you're going to do. How do I find the tangent line? What do I need?
Take the derivative.
Good, because I need what? What's it going to help me get? It's going to help me get the slope. So I need the slope. Good, so now what's f prime?
1 over x plus 1.
Good. And so what's f prime at 0?
1.
Yeah, so the slope is 1. Kick ass. Yes, sir?
Is it x?
Say what?
Is it just x?
Because what's going to be at 0, what's this? What's the point that I'm working with? 0, comma
0.
0, right? When you play 0, you get 0 out.
Oh, that's just that.
So then my tangent line is going to be y equals 1x plus 0. Yeah. So really close to 0, this approximates this. So somebody got the calculator out? Let's try natural log of, let's let x be, what do you got, Jeff? Negative 0.1. Is that cool? You guys see that?
What? You change it a little bit.
If x is negative 0.1. So really, what did we just do? Given this function, we found a linear function that's supposed to be really close to these outputs when x is close to 0. Does that make sense what I just said? That's the whole thing we just did. We found a function that's much nicer, a linear function, that gives me close enough outputs to this when the inputs are close to 0. So what did I give you? I gave you an input that was pretty damn close to 0, right? 0.1, negative 0.1. What is the natural log of 0.9? Negative what?
Should be close to 1, 0.
Negative 0.1.
1, 0.
Alright. And if I let x be negative 0.1, what's this give me?
Negative 0.1.
Negative 0.1. Is that close to?
Yeah.
So it's saying whatever I play, if this number, so what's the natural log of, what's a good approximation for this? Become a 2. You can do it. What's it say? What's a good approximation for it?
0.02.
0.02, because I know that approximation is whatever x is what the output's going to be as long as the input is
0.
close to 0. And the reason we did that whole ceiling and floor thing is to get a better feel for what the hell close means. That's come up a few times in this class. The whole idea of close is actually really controversial in some instances. Right? It's really interesting that it would be, but it is. Because what the hell's close? We're close to Alpha Centauri on the scale of all stars in the universe, but that's still pretty damn far. It would take me a while to get there. Right? Oh, yeah, so don't talk about freaking space, Jeff. And keep it to cap. Yes?
Why is it y equals x? Is it because that prime is 0 equals 1?
Well, that's the slope. And what's the y-intercept?
0.
1x plus 0.
That's a coincidence, right?
So coincidence for what? It's just, I mean...
It was like y equals x. That's what
Yeah,
we solved for it, right?
Yeah. In general, you can use this, of course, if you want to. But I didn't even have to go there because I knew the y-intercept. That's why it's nice to build it around 0, because then whatever the output is the y-intercept. That's really nice. We'll see if I'm that nice or not. Maybe. So this function, I think this is what the book called L of x, and that approximates f of x for x close to 0. That's the whole idea. It's a linear approximation. Of course, ln is curvy. So if you approximated it with some kind of parabola, it would be an even better approximation. It would be able to curve with it for a while. We got time. We can do anything. Anything. Look at the practice file. See what doesn't make sense. Oh, number 13, real quick. Little typo there. It should say 25, not 35, right? Because there is no 35 on that page. Hopefully you can get that from context.
So we give us something on optimization, but we need to do integration.
No. I mean, those problems exist, but we didn't really look at that. I don't remember there being an optimization problem with intervals. Because you can optimize, you could use that process to do volumes and stuff of rotated solids. I mean, that we didn't go into all that. I mean, that would be for later. Yeah.
Do we need to worry about 311?
Oh, 311. That was, didn't I make that extra credit?
No.
Or did I just assign it later after that
You
first?
just said we just do 5.
Oh, good. All right, there you go. But then, yeah, you should worry about it.
Or do you want those?
We should do it.
Yes. I want you to know that hyperbolics exists. And you have all the formulas to look at in the section. I mean, the basic... It's an interesting idea that instead of it being based on a circle, these are what trig functions could look like if they were based on hyperbolas. This is why we call them hyperbolic functions, right? So you could have trig functions based on squares. You could have trig functions based on ellipses. You could have, you could look that up and see what the hell that would look like. It's really neat. So I'm not gonna. It's not gonna be anything on the final about that. You just have to be able to use the formulas they gave you. I just want you to know they exist, these hyperbolic functions, and they are useful in a lot of different areas, right? But all a hyperbolic function is. So this is page 259. They have the derivatives. Page 257. They have the definition. So all we did was we collected this and we called it sinh. All right, that's the basic idea. So when they ask you to prove the derivative of sinh, you just take the derivative of this, and what you're going to get is because when you take the derivative of this, isn't that negative going to make that a positive? Yeah. Now derivative of cosh is just sinh. It's not negative sinh. So that's a departure, right? So they're not exactly like normal trig, which is why they have a little h in them, right? But they are similar in a lot of ways. That's why we gave them the names we did. I like it. So yes, tanh exists, cosec exists, sec, and cotanch. All right. But I'm not going to, beyond that, I'm not going to worry about it. You should be able to handle that section. Yes?
So sinh squared minus cosh squared equals 1, right?
Cosh squared minus sinh squared.
Cosh minus.
Yeah. So that's the analog to sine squared plus cosine squared is 1. And why does it make sense? Sine and cosine, normal sine and cosine are based on circles. And circles are x squared plus y squared equals 1, right? Or a unit circle. X is cosine, y is sine. What a hyperbola is, x squared minus y squared. So if I have trig functions based on hyperbolas, they should have a fundamental property, cosh squared minus sinh squared is 1. And they do. That's why, because they're based on hyperbolas, not circles. I mean, that's why that exists, is because it's based on circles. That's the only reason that exists. So if I based it on hyperbolas, it would have been a minus in the middle. Ooh. Well, I'm sorry, I don't mean to downplay it, but I want you to realize that we didn't have to do trig the way it was done. It makes the most sense in the world to do it that way, but you could base them on, like I said, rectangle of whatever size you want. You can make trig functions. Believe it or not, it's really neat. if anybody would actually Google that or not. Let's see. No, shit. Just watch a little animation of something that's neat, and then just go, all right, that exists. All right.
Are you give us problems on finding everything about a graph?
Like number 12?
Oh, yeah.
Yes.
How about 4 in the practice?
Number 4, the absolute.
Extreme out?
Yeah, who remembers what was nice about absolute versus local maxes and
So
mins?
you're either the biggest number or the smallest number?
Yeah, the absolute, you don't have to have a test. You just plug the endpoints and you plug in the critical numbers and you step back and you see who won. Who won for biggest and who won for smallest, right? I don't know. So the process is you find the critical numbers. How do you find critical numbers?
Is equal to 0?
Yeah, set the derivative equal to 0 or
Undefined.
derivative undefined. I like it. So that's how you find all of your critical numbers. And then you evaluate f of x at the critical numbers and the endpoints. And then you see who wins. I love it when somebody tells you 6 is bigger than 6.1 or something like that. I'm like, you do everything right at the very end. 6 is bigger than 6.1. Yeah, that's the biggest. Oh, yeah, what happened? It's just nicer, just cleaner. There's no 0.1 on it. I made it with aesthetics. I gave it an aesthetic score. So what you want to do is you want to be able to do problems like these. I'm sure I've said this before, but you never want to do something on a practice test more than twice, maybe. Because once you start doing it 3 or 4 times, you start to know that problem. And I'm not going to give you that problem, right? So you have to know problems like it. And if you haven't tried out like number 7 and number 13, they reference problems in the book. So number 7 should have some, let me see if I remember correctly. Yeah, number 5 is your related rates problem. Number 7, I think, includes a problem I have on an earlier practice test. Oh, that's optimization, yeah.
Is number 9 to include use of class?
Yeah, totally. 2 of them do. Yeah. Number 10 is weird, but I am going to kind of put that kind of problem by itself. So do you see how number 10, there's a whole little section on number 9, do these integrals, and then there's number 10. And your brain should say, there must be some reason why he put this integral all by its poor little self. And of course, what's wrong with number 10?
Number 10 has
What's up? Sorry?
number 10 has intervals and 9 doesn't.
Okay. But what's wrong with it? I mean, what?
Fraction?
Huh?
Fraction?
No. What are you going to be sure about your function if I give you intervals? And differentiable, but well, this one would be differentiable. Is that continuous, -2 to 5?
No.
No. Where's it discontinuous?
Come on.
Yeah, there we go. So,
Which means
you can't do it. The integral is undefined.
I can just write undefined.
Yeah, it does not exist. I'll take either one. You got to look for that, though. I mean, that's.
That's good to know.
What happens
Yeah.
if you didn't know that you actually solved the whole thing?
You'll come up with an answer that's completely bogus. Because what's an integral do at the end? It just looks at the endpoints of an interval, doesn't it? I mean, on one level, that should be weird. That should be really weird. That it only requires the endpoints of this interval to figure out the area between. It's like, how the hell do you do that shit? Well, all the shit we went into it. But what's its assumption it makes that allows it to do that? It's a continuous function. Yeah. That's why if without that, it goes to hell. So tomorrow, I will bring the grade sheet summary. I'll have the answer key part 2. I think that's all. You come ready.